The best braze joints are those designed with a close, uniform capillary gap. The designs for braze joints are quite different to those required for welding. In each case, the components for braze joints are overlapped to produce a narrow capillary gap. It's essential that this gap is close and uniform so that capillary attraction can operate. But what exactly does close mean? This graph shows how the strength of a braze joint varies with the clearance. It's based on joints made in stainless steel using Johnson Matthey Easy Flow brazing alloy. If the gap is ideal, say 0.05 millimeters, the peak strength is about 900 newtons per square millimeter. Even when the gap widens to 0.125, the joint will not fail at less than 600 newtons. These strengths are far in excess of the requirements for almost any brazed assembly. The way the capillary effect draws the filler metal through the joint can easily be demonstrated using two glass plates separated by 0.05 millimeter shims at the top and bottom. If the plates are dipped into a tray of colored liquid, the liquid is drawn into the capillary gap and fills it completely. This is what happens in a well-designed joint. If the gap is not ideal, the capillary effect will be diminished. In this example, the glass plates are separated by a 0.05 millimeter shim at one end and a 0.4 shim at the other. This time, when the plates are dipped in the tray, the liquid rises only part way. Capillary attraction lifts the liquid until the gap gets to about 0.15 millimeter, but then gravity prevents it rising any further. Achieving the correct capillary gap is not difficult, but it does need special consideration. In the previous demonstration, a T-joint was made by resting one part on another and holding the assembly together with a simple jig. With tube joints, a simple slip fit of one part into the other does the same thing. It gives a uniform gap of about 0.1 millimeter and allows capillary attraction to occur. But there is another aspect to be considered. When a metal is heated, it expands, and some metals expand at different rates to others. If two parts made of the same material are being joined, there's no problem. They expand together and the gap stays the same. But if dissimilar metals are being joined, such as a brass cylinder and a steel plate, allowance has to be made for differential expansion. The capillary gap at room temperature may be quite different by the time the joint reaches brazing temperature. If the joint is machined to provide a clearance of 0.05 at room temperature, by the time it's heated to brazing temperature, the gap will have completely disappeared due to the brass expanding faster than the steel. The problem can be solved by increasing the gap when the parts are cold. Now, when the assembly is heated, the brass expands faster than the steel, reducing the gap to the correct clearance at brazing temperature. If the materials were reversed, an initial undersize gap would be required. This could mean a force fit. Then, as the assembly is heated, the brass again expands faster than the steel, so that the gap is correct at brazing temperature. The amount to allow for differential expansion depends on the metals being brazed. Tables of coefficients of thermal expansion are readily available and should be consulted when designing an assembly. So to summarize, we need the correct joint design, a close and uniform gap, and that gap to be correct at brazing temperature. Now let's move on to the second basic step in successful brazing, the choice of filler metal.